Welcome to the 5th year of the Science Within Society lecture series. My name is Gay Allison, and I'm the Associate Director for the Montana NSF EPSCoR program. Now, if you're like me, acronyms seem to be an everyday word now, or, well, words, whatever. And experimental program to stimulate competitive research is what EPSCoR is. What that is federally mandated money from Congress that goes to states that are underfunded in the sciences. Montana is one of those. And this money has been available since 1980. All the federal agencies have a portion of that. NSF has the largest portion. We compete along with 26 other jurisdictions. Those are states. That's their fancy word for it. Puerto Rico and the Virgin Islands are part of that. It's a $9 million award over 3 years, and it requires a match. So we go to the state and ask that they help us. And so for every $1 they give us, we get $2 from NSF. And they have supported us since 2001. So right now we are in our 2nd year of a grant that started in 2004, which will end in July of '07. And we have a $13.5 million grant. And one of those projects funds Science Within Society. So before we get into that and our guest lectures, I have to give you some statistics because this is, okay. And we've just finishing this 2nd year, the University of Montana, Montana State University, all the tribal colleges, and Montana Tech buy into this partnership. And to date, for just these 2 years, we have funded 37 new faculty hires, 4 tribal college hires, 74 PhD graduate fellowships, 481 undergraduate fellowships, startup funding of nearly $500,000 for small competitive research business opportunities that people in the university who partner with people in the state build small businesses. Right now we're running 18 programs in the state. And Science Within Society is one of our outreach programs. There's some literature up here which you're free to take at the end if you like. This fella on this one came and he did a Science Within Society lecture on Blackfeet skies. We also have produced a graduate recruitment DVD. 10,000 of these went out across the country to get people to come here to go to school. And if you're up early on Saturday mornings, you might hear on the Children's Corner, Science is Cool with Dr. Katie George. And we've produced CDs with all of their science projects that they do on the air so kids can do these at home. And we sent these out to all the public schools and all the public libraries in the state. So that's what we do. And we underwrite this, and we're so very happy that you're all here. Please stay for the reception and talk to our guest lecturer and get to know our program a little. And now I'd like to introduce Dr. Eric Green, who's the Associate Director for Division of Biological Sciences, who will introduce our guest lecturer. Thanks so much for coming.
Thanks, Gay, and thank you very much to EPSCoR and NSF for helping host this. And I can't tell you how delighted I am to introduce Dr. Gary Vermeij. He's one of my, I know you don't hate this word, but one of my longtime role models. I started reading papers by this guy when I was a student and thought they were the neatest things, really elegant blend of natural history and big ideas and careful observation and synthesis and new ideas, and he's been going at it ever since. we're really lucky to have Dr. Vermeij here. He was born in the Netherlands, and he and his family came over to the States when he was pretty young. He did his undergraduate at Princeton University and did his graduate work at Yale. And he's renowned for his work on shells and well, it's hard to describe what he does, and you'll hear all about it, but he thinks so broadly and widely. We're really lucky he's a member of the National Academy of Sciences. Well, he was awarded the Daniel Elliott Medal of the National Academy of Sciences, which is one of its highest awards. He received a MacArthur Fellowship in recognition of his work, and he's got hundreds of publications, influential publications, technical publications, some really neat books. Here's three of my favorites: Biogeography and Adaptation, Evolution and Escalation, and his most recent book, which I'd really recommend you take a look at if you're interested in this stuff, Nature and Economic History. And it's a really neat blending of ideas from biology and blending it with thinking about economics and competition and how interactions in general work within the biological and world and societies. One of the things that I've admired most about Dr. Vermeij is the way he combines really keen observation skills. It's really clear, and you'll see in a few minutes, he's an amazing observer of the natural world. And all of the people in biology who inspire me, I think, tend to first and foremost be really good natural historians. But then beyond that, Dr. Vermeij is outstanding at taking what he observes of the natural world and thinking broadly and deeply about these observations and putting them together in new, broad, synthetic ways and really exciting sorts of things. So that's what he's going to talk about a little bit tonight, and I'd just like to say thank you, Gary and Edith, for making the trip here, and we're really delighted. I should also mention that Dr. Vermeij has been participating in all this week in Camp Eureka, which you may have heard about. This is a really exciting camp that's in its second year now. It's a camp for blind and visually impaired kids from around Montana and neighboring states. It's a sort of nature camp. It brings kids together, and it's begun last year as an experiment and succeeded beyond our wildest dreams. And Gary was volunteered to come down and help out with this camp. So he's been spending a week up the Bitterroot at Teller Wildlife Refuge at this camp with the kids, and really teaching them natural history observation skills. So it's been really neat. Thank you.
Thank you very much, Eric, and I really appreciate the visit, I must say. It's my second time to this state, and it's wonderful, I have to say. So today we're going to take a journey, if you will, from the study of shells as objects of pure aesthetics to what I hope you will see as big principles of evolution and economics. And we're going to talk a bit about what shells and in general nature tell us about our past and our future. Well, I've always loved natural history from essentially day one. As Eric pointed out, I grew up partly in the Netherlands, where we were just well off enough to visit the beaches of the North Sea on occasion. And there I enjoyed very much picking up lots and lots of shells on the beach. And all these shells, chalky and ordinary as they were, really did capture some imagination. However, when I came to the United States, a year after I came, I had a fourth grade teacher who took her vacations in Florida, and she brought back shells that she picked up on the beaches there, and she brought them to her classroom, where I had a great deal of time to kill. And fortunately, she left these shells out, and I was utterly enthralled because we had shells that were so neat. Here's one. This is a whelk. It's got this crazy long point. It has beautiful things, ridges inside. It was this kind of shell that I had never, ever seen before. And from that point on, I was bitten by the bug of wanting to be first a conchologist, somebody who studied shells, then a biologist, and then later just a scientist. And fortunately, that's how it came to be. So for me, shells originally were objects of beauty, objects that were simply aesthetically pleasing to me. So I want you all to come up and look at these shells I've got here, which are fossil shells, actually. But one of the ones that really got me from the beginning is this sort of cowrie. This is a fossil, so it isn't glossy anymore, but the living ones are very glossy on the outside, and I used to think that it was people who varnish shells completely to death. And of course, I learned that wasn't the case at all. I also couldn't believe how any shell could have this narrow opening at all. It was just inconceivable. But for me, they were objects of art. And I have to say that one of the reasons I continue to study and to collect shells is because of their enormous aesthetic beauty and diversity. I mean, this is a wonderful object, this big Trochus niloticus from Guam. It's a wonderful object. It's smooth inside. It's got its neat shape. It's angular. It's aesthetically greatly pleasing. But as I say, I began by studying shells as isolated objects of nature. For me, they were beautiful, and that was it. But of course, shells are more than that. They are actually parts of animals. Animals built these shells. Animals are surrounded by these shells, or occasionally, shells are surrounded by animals, as in the case of the cowrie. But the point is that we're not just talking about shells, we're talking about living animals. And that means making your way in the world. Now that sounds cosmic and touchy-feely and all the rest of it, but actually, when we start thinking about shells in this way, we realize that they are functional structures. And that gets us into the subjects of ecology and economics. Well, those two words have the same prefix, which is derived from the Greek meaning, the Greek word oikos, which is house. And what else is a shell but a house? So what we're really studying is not only the study of houses, but in some sense the study of homemaking, the study of how you make a living in a world that is difficult. Well, of course, I didn't have this insight straight away. I mean, we finally started going to some of the beaches in New Jersey, and I finally got to see some living snails and some living clams and some horseshoe crabs, and slowly but surely it dawned on me that these snails and clams, the ones I was really interested in, have to make a living in a world that is effectively dangerous. So, for example, here's a scar, a hideous break that this animal suffered during its lifetime. The shell was broken back, we think, by a crab. The animal that built this shell survived and continued. It repaired this break, not necessarily very neatly, you can look at this later, but then it went on and on and on to grow here until it died. What that shell tells us, it basically wrote a diary of its life. It began life up here, and it goes around and around and around in a spiral, in a beautiful spiral that nearly, but not quite, obeys the rule of the logarithmic spiral. And while it was growing and living its daily life, it was attacked, it survived, and the shell now tells us that story of being attacked and of surviving to grow a lot more. So we know that this animal suffered the danger of enemies. Now, when I was a kid, one of my family members, my brother, in fact, gave me a specimen, a shell. And it was a conus, a beautiful cone shell, except for one thing. It had one of these horrible scars on it. And I thought it was the ugliest thing in the world. But I couldn't tell him, of course. But now, I look back on that cone, and I think to myself, this cone could have taught me a lesson about the biology of these animals. Of course, it didn't at the time, but now it does. And so I began slowly to realize that shells could tell me not only about what kinds of dangers animals face today, but if I looked at fossil representatives, I could learn about the conditions of the distant past by looking at the architecture as well as the daily history of individual shells living at different times in Earth history. So in other words, shells became more than just objects of interest and objects of beauty and of geometrical regularity. They became now objects that told me about a larger world. I began to see an ecology of the present and an ecology of the past as told by the architectures and the daily lives of ancient and living mollusks. So I began to do a very boring dissertation. It's not my best work, at least I got it published. But while I was doing my dissertation, I went to Guam. And one day on the reef flat, I picked up a dead cowrie, one of these, except that the top was all broken away. And of course I thought, no, we don't want that. And the man who was with me, a very excellent natural historian named Lou Eldridge, said, well, these shells, it was very fresh. It was all glossy smooth as if it died yesterday. And he said, oh, crabs do that. And I said, oh, really? And I sort of tucked that away in my memory. I probably wrote it down that evening in my scientific notebook, which I maintain. And I sort of thought about it. And I thought, well, suppose crabs were common in Guam, which of course they were. And suppose that all of these architectures that I'm seeing around me are really adaptations to dealing with animals that break and crush shells the way these crabs were supposed to have done. And indeed, all kinds of lights went on, in a metaphorical sense, of course. And so I began a long study of, much of it done with my wife, Edith Zipser, of how crabs actually break shells and which features actually prevented shells from breaking. And that work slowly expanded to some fish and to other snails that eat other snails, and so on. So I began to gain a general understanding of what predators do to snails and clams. Well, it was all well and good to understand what breaks what, but a key part of this story really is not how animals die, but rather how animals survive, because that, after all, is what evolution, of course, is all about. Now, evolution is really nothing more than descent with modification. It doesn't tell you what the mechanism is. It simply says that organisms that are the descendants of ancestors have changed relative to those ancestors. And it's up to us to figure out why, how, in which directions, and so on. So the key, of course, is survival. Think about this. Every single organism living on Earth today, including, of course, all human beings, are the endpoints, we hope not the end points, but the most recent points of an unbroken line of descent that goes back to perhaps 3.5 billion years ago. That's a lot of generations. It's a lot of success. Evolution is built on success. We have suffered over the course of the past, that long, multiple crises that led to the extinctions of many, many creatures. But all of us living on Earth today have ancestors that lived through every single one of those crises. That's an awesome idea, because what it tells us is that organisms living today are not only adapted to the everyday conditions of competition and predators and so on, but also to the more unusual attributes, the things that come along every now and then. And when I say now and then, it could be every couple of 100 million years in some cases. They may not be specifically adapted to those conditions, but they are adapted, they are, if you will, predisposed to be able to deal with those extremely rare and unpredictable events. Well, one of the common events, of course, as I've tried to point out, is predation. And so here we have evidence that this animal survived a pretty substantial attack by a predator. Therefore, we can say that something about this shell was good enough, was sufficient to withstand that kind of moderately common onslaught. So in other words, this shell should have adaptations to deal with that fairly quotidian, everyday phenomenon such as predation. And indeed, if you start looking at shell architectures, you start seeing all of a sudden a whole range of features, some of which are heavily armored features, and some of which have features related to speed. So, for example, here's a fossil ammonite, which Eric Green kindly lent me. It's a Cretaceous ammonite. It's a fossil. It's about 70 million years old. It was a swimming, distant relative of a squid. You can see it has big ribs all around here. Actually, it was a very thin shell, but very sturdy. Here's the other side, it's symmetrical. The animal swam around. It was probably not incredibly fast, but it was fast enough. But it was also fairly heavily armored. Well, the ammonites unfortunately became extinct at the end of what we call the Mesozoic era, which we could translate, if you will, as the Middle Ages of life. So if I had been an ammonite at that time, I could say, I am a knight in armor. And as you know, they became extinct at the end of the Middle Ages. So there we are. Pretty bad. So that is a combination of emphasizing armor and emphasizing speed. Here's a snail. This one too has a wonderful scar on it indicating some damage. This is a fossil 2 million years old from Florida, but it's also fairly fast. It has a rather big foot, as indicated by this aperture. It's smooth. It moved fairly quickly. So for any given problem, there are multiple solutions. In the case of mollusks, we can think of those that have armor, which is sort of a resistance kind of defense. We can think of organisms that use aggression. We know altogether too many examples of that. We have examples of animals that flee from their enemies. We have animals that have very good senses so that they can detect danger before it arrives, and so on. So there are many, many choices. And we can identify many of those choices in fossil materials. In particular, of course, we can also count scars left by unsuccessful predators. Now, I said a moment ago that evolution is the story of success, but I actually could turn this around and say that evolution is also the story of failure. Because if we are to adapt to our enemies, we have to survive to tell the tale, which means that the enemies have to fail, at least sometimes. So every unsuccessful attack from the predator's point of view is a successful attack on this thing, right? It means that this animal survived. The predator just had to go on and break something else and hope for the dinner the next time. But in other words, success and failure have to go hand in hand. If every attack were successful, then the victim species wouldn't be around anymore, or else it reproduces so quickly that it didn't matter anymore. But the fact is that you cannot adapt to a predator unless that predator fails quite often. And fortunately, as a survey of the literature will indicate, they often do fail at a very high rate. So when Edith and I worked on crabs in Guam, one particular kind of crab that likes sand-dwelling mollusks, which it breaks open by peeling away the outer lip of the shell, it turns out that 91% of their attacks end in failure. That must be frustrating. Paul Dayton at Scripps documented a case of a sea star in Chile which hunts snails, and every time it approaches those snails, the snails fall off the rocks. They feel them coming, or they hear them coming, we don't know which. But the point is that 99% of those snails survive, and only 1% are caught. Incredibly frustrating. Studies of hawks and eagles also indicate that most of their attacks fail. There's a famous study back in the 1970s by Schaller on lions in the Serengeti in East Africa, showing that about 1/3 of lion attacks result in failure for the lion. That's good news for us. Well, so we can actually go back in time, in geological time, and look at scars of mollusks, and also look at architecture of mollusks, and we can say something about the predators that were major agencies of selection. And something quite interesting happened. Here we have a shell with a really narrow opening, a cowrie. Very, very narrow opening, which has teeth along both lips. It's hard to get into. The shell is also hard to break. If you go back 200 million years ago and earlier, that kind of architecture, that kind of house, does not exist at all. Today, in parts of the Western Pacific and Indian Oceans, something like half the snail species that are larger than 5 millimeters in length will have some version of that architecture. So in other words, things have really changed. And in fact, in another study that we did, my wife Edith and I and a colleague, David Schindel, back in 1981, we counted the scars on shells from 5 different fossil assemblages, and we found, quite frankly, to our own astonishment, that the incidence of those scars increased through time, which all these observations together suggest that the predators that break shells have gotten bigger and stronger over geological time, that certain kinds of architecture that are common today were virtually rare or absent in the distant past, partly because they just weren't, quite frankly, quote, necessary, unquote, whereas other architectures that make the shell vulnerable to breakage greatly declined in frequency. So it looked as if there's a certain escalation going on between predators and prey. Well, escalation, of course, is a military term, and we all know it. For those of us who know the Cold War, which I guess is ever a diminishing number now, when we had been publishing this kind of stuff in the early 1980s, and then Ronald Reagan came on the scene and promised us an anti-ballistic missile system that would intercept 100% of the incoming missiles. And a red flag was raised because nowhere in biology is anything that perfect. Imperfection, failure, is the rule in biology. You can't build a perfect defense system, and you can't build a perfect offensive system no matter what you do, for a very simple, straightforward reason. Your enemy will find ways around it. So it was, in a sense, a dangerous ruse built out of a complete lack of understanding of evolutionary and indeed economic principles. Well, at that time, of course, we were engaged in a gruesome arms race with the Soviet Union. And I was interested at that time in particular in how would you stop such an arms race? But then the question quickly arose, how do you start an arms race? And how does biology tell us something about this? Well, we have 500 million years of history of mollusks, the animals that build shells, to work with here. And so we have lots of history, lots of time. What does that history really tell us? Well, I'm not going to go into this in great detail, but it looks as if the times when the greatest armament advances arose were those when the world's ecosystems were, on a very large scale, enormously productive. When also conditions in the world were warm. Now, remember those Dutch beaches and the Florida shells? One of the biggest differences there is that Dutch beaches are cold, just like Montana rivers, as I should know by now. Whereas Florida beaches are warm. And I happen to love the tropics, not only because I basically love warm weather, but also because the animals that live there are so much more diverse in warm waters and in warm climates generally, and plants too. And why is that? Because everything in biology speeds up in higher temperatures. And not only that, but certain expenses that organisms have go down. So for example, if you swam in a warm swimming pool, you would be using less power for a given speed than you do in a cold swimming pool. And the reason is that the so-called stickiness or viscosity of the water decreases with temperature. That means you're expending less energy per unit time as you go through that water. That's only one of many kinds of expenses that are spared for warm water creatures, which means that you have more options available when you live at high temperatures as compared to when you live at low temperatures. Which means that when the world in general was warm, when warm areas extended over much larger parts of the globe than they do today, it means that organisms had much more scope for evolving fancy adaptations to any number of problems than they do when much of the Earth's surface is cold. So the periods of time, and we have documentation for this fairly extensively, those periods of time when warm zones were large, when temperatures were high, when productivity in the world's ecosystems was generally high, those are the times when we see lots of novelties arising, lots of new features, lots of new adaptive ways of dealing with your enemies, and as opposed to times which are relatively cold. Now, predation is only one form of a very general and fundamental economic principle, and that is competition. Now, for me, what is important as an evolutionary biologist is that competition is essentially a universal attribute of all economic systems. And when I say competition, I mean that two or more living things are trying to obtain or trying to defend the same locally limiting resource. The example I love to give derives from having had a child. Children, nowadays especially, seem to have an oversupply of toys. So toys are not globally a limiting resource anymore. However, when you have two children who want to play with the same toy at the same time, the single toy becomes a locally limiting resource and aggression breaks out. And there is competition, fortunately without fitness consequences. But nonetheless, it gives you the point that I want to make, which is that things even like oxygen and carbon absolutely universal, common, everyday elements, parts of living molecules, can be in short supply locally, and organisms are going to be competing for it. Now, there are multiple strategies for doing this, one of which, a crucial one for the origins of life and for much of life since then, is cooperation. Cooperation, I hate to tell you, is not a real antidote to competition, at least not in the large scale. Yes, it may help those who cooperate. They're no longer competing. But meanwhile, what you've created is a new, more powerfully competitive entity consisting of cooperating individuals. So what I'm getting to is that the study of shells, in effect, is also the study of economics. And not just because we're studying houses, but also because we're studying how animals and plants, of course including mollusks among the animals, how they are gaining and defending resources. So economics is all about how resources are allocated. That's really what economics is about. It's an enormous structure of mathematics, complex theory, but it all boils down to just a very few principles, the most important of which is competition. Well, I suggested to you that the greatest novelties in biology arose at times when organisms found themselves in warm, productive environments where there are plenty of predictable resources. And when those resources don't exist, or when they become unpredictable, or when they're difficult to gain access to, then all of a sudden, just as you have with a declining budget, you can't really do anything new. Why? Because if you spend more money on one thing, you're going to have to take it out of something else. Whereas if a system is growing, or if it's highly productive, well, then everybody can have their cake and eat it too, at least to some extent. So in other words, this is what economists refer to as opportunity costs. So what you have is when resources are really quite sparse or difficult to gain access to, what you get is that the best solution to that problem is the status quo. So those of us who are scientists and who are trying to get funds from the National Science Foundation find that there is extremely little money out there for us, that only about 10% of grants are funded. So what's the best strategy? Well, the best strategy is not innovation. The best strategy is do what's been done before because it works. And that is, in fact, the case. So, what does that tell us? What does that tell us about our future? Well, there's a lot of interesting stuff here. Human society, for the past 400 years or so, has been in a more or less constant condition of population growth and of per capita economic growth. So much so, in fact, that economists have become rather addicted to it, whether they're communists or capitalists, free marketeers or regulators. They all believe in growth, and for a very good reason. I myself benefited from a society that was growing. Had I lived in the 18th century, when growth was much slower than today, or had I lived in the Middle Ages, believe me, there would not have been money set aside to educate the blind, perhaps even to keep the blind alive. But with a relatively wealthy society, society found monies worth it to educate blind people. What I'm really trying to get at is that growth is something that gives opportunity to explore many adaptive pathways in biology that allows for innovation. And economists who study the history of innovation have come to conclusions remarkably like the ones that I have reached from a completely different direction, namely the direction of the history of life. So, the problem, of course, is that you can't grow forever. No matter how many times we can change resources, coal for wood, oil for coal, and perhaps who knows what for oil, sooner or later the Earth will reach a certain point of saturation. So it's time to think about what the world would be like without economic growth. Now, many people, of course, would like to see a world of non-growth, and I have to admit that in a philosophical way I kind of agree with that position. However, if human history is at all like the history of other organisms, as I maintain that it is, well, then there's one pretty obvious thing in the future, and that is that our responses will become conservative responses. We will do what we did before because it worked in the past. The status quo is the best solution. Not more opportunities, nor greater innovation. So, knowing that this is pretty much the case, we would be very well off trying to construct an economic order in which we retain the provision of opportunity and the provision of some degree of flexibility, even though we may not all be able to grow. Now, I've made sort of oblique mention to the idea of a parallel between the history of life and the history of humanity. And I suggested to you that the armaments and the degree of locomotor performance of mollusks, the things that I study, these effete, worthless objects that only scientists like me are interested in, that these things give us a picture of history suggesting escalation between enemies and their victims. We see that we can identify the conditions that are most favorable to change. We also see great parallels between human and non-human history. After all, escalation pervades human history as well for the same reasons. We compete. Societies compete. Societies come together. Societies are bound together by certain cultural norms which make societies more cohesive, more powerful. And one of those features, by the way, is a shared religious faith, whether I like it or not. The kind of change that we observe in human history is occurring over a short term, over the course of thousands of years, and in some cases hundreds of years or even decades. That, in the history of life, on the other hand, is taking place over millions to billions of years. But it's the same idea. And why? Because the same economic principles are involved. Competition is one. Organisms compete for locally limiting resources. Feedback is another. Organisms adapt to their environment, as we've seen with these mollusks, but they also create their own environment. And so there's a feedback between organism and environment. As we all know, it's different from walking around in a forest from walking around in a prairie. And that's only because organisms have changed the microclimates in which we walk. And then there are fundamental ideas about inequality. Enemies, such as the animals that prey on my mollusks, have had a disproportionate effect, not only on the architectures and on the performance levels of organisms, but also on the distribution of organisms. So here's this ammonite again. Poor thing, we don't have any shell-bearing cephalopods except for one, well, maybe two genera, a total of 5 different kinds of cephalopods that have an external shell the way these ammonites had. This architecture at one time worked just fine. And they armored themselves. They've got knobs here and so forth. And this characterizes a lot of late Cretaceous ammonites close to the end of their existence. But sooner or later, this architecture simply didn't work anymore. It became obsolete. The shapes that worked for at one time no longer work, except perhaps in a very few relictual or refugial environments. So whereas we used to have shell-bearing cephalopods like this all over the world, throughout the oceans, today the one genus that survives lives in a rather restricted environment in front of reefs in the Pacific Ocean. So in other words, they became restricted because they otherwise really can't measure up in other places. So we see all these parallels occurring in human history as well. And again, it's because the same economic principles are acting. Now, humans are the most powerful species per capita and collectively that has ever existed on Earth. We're probably among a handful of species that has been able to cause the extinction of many other species. We have modified the environment more than any other species has. Well, if you look at the great span of geological history, we see that the human species is obviously the most powerful, and I might say the most recent among the dominant species. If you look on land, of course, we used to have dinosaurs. And before we had dinosaurs, we had earlier reptiles, and we had mammal-like reptiles, and then we had amphibians. And as we go back in time, the dominant, the most powerful, the largest species become increasingly less powerful. Or, to put it in a more reasonable way, if you go forward in time, the organisms that had the most effects on their victims become increasingly powerful. Humans are the pinnacle of that. And within humans, of course, we see that modern humans are more powerful by far than even those 100 years ago. So we're seeing the same directionalities in history that repeated in the human framework that we see in the history of life. What does that mean? Why should that be so, besides those fundamental economic principles that have kind of drummed into your head? Well, it's also because some of the features that make organisms powerful are the same each time. So in other words, some adaptations are so broadly applicable, such as intelligence, such as heavy armor, such as rapid locomotion, that they are going to arise time and time and time again, which gives evolution, just like the human history, a certain predictability. Now, we cannot predict exactly who's going to do what, when, or where. But in the long span of things, we can say that certain things are probably going to happen. This provides history a directionality. Stephen Jay Gould, whom I knew quite well, had this famous line that if you ran the tape of life back and you ran it again, it wouldn't look anything like the instantiation we have today. I disagree with that. I think the players would be different, the timing would be different, the places where evolution happens would probably be different, but the outcomes, I think we would recognize them. And that's because the same principles apply all over the place, human, non-human, whatever. So we've come a long way from shells, in a way, although I have to tell you, I'm still working on shells and love every microsecond of it. But shells are more than just beautiful objects. They provide us with a window on the present, on the past, and I'd like to think on the future. Thank you very much. Also, I'd love for you to come up and look at some of these things. They are nice objects. They're all 2 million years old from Florida. And of course, I'd like questions.
And before I forget, let me just say that after this, there's going to be a reception outside with ice cream and cookie and coffee. So that'll give us more of a chance to mingle and chat with Dr. Vermeij there too.
You know what I tell my students? If you don't say anything, it means you agree with everything I've said.
Well, I just wanted to tell you that I have a cone shell, which I understand comes from only one place, and that's on the west coast of Baja California. It's not as large or as heavy as the one that you have, and people tend to polish it down so that it shines nice, but the one I have, I haven't done anything like that, and I got it when I was down there, but it was my understanding it only came from the west coast of Baja California.
Well, there are actually very few organisms that live only on the west coast of Baja California. I know of about 2 or 3, and I don't think the cones are among them. Most of them have a broader distribution that would include the Gulf of California and further south to Panama and Peru and so forth. And there is one species that extends from approximately Central California down to somewhere in Baja. I'm not quite sure where. And that's the only one that makes it into the temperate zone of California.
Question about evolution of man. This might be kind of a big question, but where do you see the evolution of humans going? Maybe specifically, do you see gene manipulation as a factor in human evolution?
Okay, the question is, where do I see evolution of humans going, and is gene manipulation going to be a big deal? I think for the moment, much of human evolution is cultural, and it has been probably for the last 11,000 years. We are undergoing some genetic changes too, but I think these are extremely minor compared to all the cultural things. And I have to say, I don't really distinguish all that much between cultural and genetic evolution, except that cultural evolution is much faster. Cultural evolution was not invented by humans. It's been around a long time. Animals have learned and changed culturally for a long time. As for gene manipulation, I think in the long run, probably that will turn out to be very important, as will a lot of other genetic engineering. And although humans are probably capable of a great deal more genetic engineering than anybody else has ever been able to do, nevertheless, gene transfer is probably a characteristic of life from the very beginning. So we should be careful in all that, but we should not delude ourselves into thinking that we've invented a whole new thing.
Are you concerned about the disappearance of seashells? We lived on the island of Grenada in the Caribbean, and we used to find like the Musica Velut.
Yes.
Of course you are. And they're nowhere to be found now, and many of the other species have totally disappeared. And that's just a minuscule area of the world. What is happening overall with the disappearance of seashells?
As far as I know, there have been few actual extinctions, but anyone, including myself, who has been collecting over the years will have the same story you do, which is things that used to be common are no longer common. The main reason is probably human exploitation and to some extent human degradation of environments. Yes, I'm deeply concerned about it. Anyone who is involved in with living organisms, marine, freshwater, or terrestrial, is going to be concerned about it. It's a huge problem. We are unquestionably contributing to it, and the solutions are not incredibly obvious, but it's a huge problem. There's no question. As we increase our per capita wealth and our population around the world, we are putting ever more pressure on species. We are restricting them. And there's something quite interesting. You know, I said that growth enables evolution and adaptation. What we're doing to most species in most parts of the world is we are restricting and diminishing their populations, which means that we are really, in effect, preventing their adaptation. And that, in the long run, is probably the worst thing we're doing. In the short run, it's purely overexploitation.
I was curious as if too, you had also studied the shells and how they record the climate at all?
Oh, yes. We study that, and we study seasonality. There are techniques, and I had a graduate student, Greg Herbert, do this a few years ago, and I had another one named Michael Kirby who did the same kind of study. You can actually look at the ratio between two isotopes of carbon or two isotopes of oxygen and you can take a section of a shell. So if you were taking here's a bivalve shell, here's the oldest part, and you take a section down here, and you can look at the seasonal change in isotopes and count how many days old it was, or how many years old it was, and within that time you can also read the temperature to some degree, if that is to say the mineral content hasn't changed very much. So yeah, that's a very active area of research. The kicker is that the mineralogy of the shell, the mineral composition of the shell, has to be essentially as it was when the animal died, and it cannot have changed a great deal, otherwise you will get noise and meaningless data. But yes, people are doing that, and it's all very interesting.
Does it support global warming? Are you seeing a pattern with it?
You know, the complete truth of that matter is that I think very few people have studied this, and it would be an obvious thing to do. Somebody should go and look at old museum specimens of living species and do some sectioning and do some temperature calculations, and from the same locality as specimens that are collecting today. To my knowledge, that hasn't been done. But let me tell you right now that the evidence for global warming is, in my estimation at least, overwhelming. For those of us who have lived on Earth any length of time, I think most of us realize the weather has really gotten warmer in most parts of the world. And there's also no question in my mind, or in the minds of most other scientists, that responsible for this is an increase in greenhouse gases, which are being liberated either directly or, in many cases, indirectly by human exploitation.
You talk about the fundamentals of ecology and our economic system in the perspective of these fossils. I want to know your opinion on the exponential growth. You speak of growth, and that is good for adaptation, but in the human sense, what do you think of it?
I'm afraid I would still say that's true. So in other words, the question is, do I think that growth, economic growth, effectively is good for human adaptation? I think the answer must be yes, because if you look at major social advances, major scientific advances, these tend to occur and are partly responsible for, there's a feedback involved here, tend to occur after and before periods of economic growth. And again, I think the principle underlying this is quite simple. Most major innovations cost a lot of money. There's a lot of capital involved, a lot of resource investment involved. That's harder to do if outlays in those directions directly reduce outlays in other directions. So it's purely, in a sense, a statistical argument, which is that you're more likely to, quote, experiment, unquote, or to do something risky and new if the penalty isn't death. And I think that's really very, very powerful. And so I think, governments would have a harder time spending money, and this is why the Soviet Union in many ways was really killed. Their economy was in terrible shape in the 1980s. And then essentially, whether I like it or not, and I don't, Reagan forced them to spend all this money on unnecessary nuclear weapons, and it killed them effectively. And they're still reeling from that. I don't think they've really recovered from that disaster. So yes, I'm afraid to say it doesn't have to be exponential growth. It doesn't have to be 2, 4, 8, 16. But I think some degree of growth is probably necessary.
I think I hear you saying that economic growth for humans is not necessarily economic growth for plants or animals.
That is certainly true. Although, here again, there's no doubt that we are greatly constricting many species. But let me say, this is nothing new. When I'm sure that many plants were very, quote, unhappy, if you will, if they had emotions, which of course they don't, but they were probably not really very happy when 55 million years ago we had the first large herbivorous mammals, right? So the problem is that dominant groups that have unusual ecological power have many negative consequences. So, for example, there used to be a whole group of clam-like animals called brachiopods that lay immobile on the sea surface. But when a whole lot of predators and perhaps competitors came along, this lifestyle became anachronistic, and they disappeared. Maybe not directly because of competition, probably for some other reason, but the fact is they couldn't recover. So, yes, economic growth for us is probably translated into economic depression for others. However, there is a peculiar and interesting side effect to this. Again, we may not like this, but agricultural production has increased even faster than human population growth, which means that we are making ecosystems worldwide now far more productive than they've ever been. In the same way, when bison defecated all over the prairies, they were speeding up production of grasses. And speeding up production means increased production. It means increased productivity. It means increased power. So you have this mischievous effect that the dominant organisms are hurting some species and helping others, and meanwhile just changing the landscape. So it is certainly true that we are probably on average hurting the great majority of species. But on a global scale, we've probably increased productivity. And, if there were enough time, and of course we're living short-term lives and we can't really think in long terms, but in the long term, that may actually be good.
Gerrat, has the economy ever experienced anything like a mass extinction? And in terms of the kind of things that happened?
I would say that it has. If you read accounts of the demise of major civilizations, for example, the Maya civilization in about 800 AD, or whatever they call it nowadays, whatever the politically correct term is, BSC or something, I can't remember what it is. Anyway, or if you look at the demise of the Mycenaeans, 1500 BC, and all these others, many of them are the consequences of overexploiting soils, of great droughts, which make that overexploitation worse. Sometimes it's volcanic eruptions. So yes, there are examples that at least parallel the story for mass extinctions. Mass extinctions are very interesting because they are all caused, one way or another, by catastrophic declines in the productivity of the ecosystem. What basically happens is that the bottom falls out of the production system, and so everything else tumbles. The one exception to that is the end Pleistocene, when humans got to North and South America and Australia, and they started killing off large top predators and top herbivores among the mammals, for example. That's a top-down kind of extinction. But the great majority of geological extinctions are bottom-up, so the bottom fell out of the system. And I think that's extremely parallel to many of the great crises in human history as well. Even the Little Ice Age had this catastrophic effect in places like Greenland, and among the Navajo in North America. So yeah, I think there are very definitely parallels.
Do you ever eat mollusks?
Rarely. I happen to have eaten one tonight. I don't usually care for them. I don't like them in terms of flavor. But I'm not philosophically set against it. The only reason, by the way, that there are reasons not to eat these things, and most of them have to do with what the collateral damage is. So, for example, much as I love shrimp, I will generally not eat it because the means that people use for either raising shrimp or for fishing for them, for catching them, that use so much damage to the rest of the environment that it just is irresponsible, in my opinion. Unfortunately, a lot of what we do is that way, and we can't be too fussy about it because otherwise we wouldn't survive, and that's just stupid in a way. But nonetheless, I think there are some kinds of exploitation that just are not supportable, and I'm afraid I think shrimping is one of them.
Please join me in thanking Dr. Vermeij. come up and have a look at some of these amazing shells, and then we can adjourn to the ice cream.